very important role because whenever you are trying to do something and randomness is involved, that means there will always be a probability of happening or not happening of the event. So you always want to compute different types of probabilities and you want to approximate different types of statistical distribution. Now, in such a bigger data set where you have millions and billions of observations, or even say this a couple of lakhs of observations, I think this means computing the exact probabilities. For example, if you have to compute the probability using binomial distribution or Poisson distribution, that is very difficult. I mean, the software is not difficult conceptually. Conceptually, one can do it, but software will not be able to find out those values. For example, if I say 5 million choose say 10,000. Right, this value is mathematically well defined, but no software can compute such a value. Right, so that is why this normal distribution plays a very important role, and I will try to just give you an idea of the role of normal distribution in data science, and that is why I have chosen this topic. And based on that, how we try to draw different types of inference. Right, okay, so this is one of the most popular distribution in probability theory, and if you try to see, many times people get a very simple question that how do you know that the process is going to follow a normal distribution? So let me try to take a very simple example. I will try to show you here. You just try to, miss, I cannot see you. I'm watching only my slides and I cannot even see myself, but still I will try to do it. You see, in your home, so you are always trying to, your mom and your family member, they are trying to cook some vegetable curry for you. So let us try to assume that the taste of vegetable curry is a function of the quantity of salt in that curry. So now if you try to observe this process and try to plot the curve of this process, how it will look like. On the x-axis, you can say take the taste, and on y-axis, you can take the quantity of on the x-axis, you try to take the quantity of salt, and in the y-axis, you try to take the taste. So when the quantity of salt is 0, then the taste is 0, means under the normal conditions, means I'm trying to say. Right, so usually a common person will say, no, there is no taste, there is no salt. Now you try to increase the quantity of the salt, the taste will start improving. What will happen? So on the x-axis, you are trying to increase the quantity of the salt, and on the y-axis, the taste is increasing. So what will happen? The taste will start increasing as the quantity of salt increases, and it will reach to a maximum. And after that, it will start decreasing. I mean, the taste will become the maximum when there is an optimum quantity of the salt. And after that, if you try to increase the quantity of the salt, then the taste will start decreasing. And finally, that there will be too much of salt in the curry that nobody can eat it. So if you try to see, this shape is going like this, a symmetric L-shaped curve. Right. So this type of thing, and if you try to see most of the processes in real life, many processes are following this type of curve. Even the human being also, I mean, the person starts when the person has no strength, that person cannot do anything. The child cannot walk, cannot take the food. He's or she's depending on his family. Then the strength starts increasing, the children grow up, they will have the maximum energy, and after some time the energy also starts decreasing, and finally we come back to the same condition as we were born, that in the old age when we are unable to do anything, we are completely dependent on the family. So this is also a very good example of the process which will look like a symmetric curve. So this normal distribution is also called as a Gaussian distribution, and it has become very important, or it has found a very important role, particularly in data sciences, because of center limit theorem. What is that? I will try to discuss here. So this is the mathematical function which is trying to describe such a symmetrical bell-shaped curve. So it is as simple as that. We always have the curve like y equal to mx plus c that will describe a straight line. So similarly, this is also a function which is dependent on two values, mu and sigma square. So mu and sigma square are the parameters of this distribution which are trying to characterize the features and properties of this distribution. For example, if you try to see here, when we say mu and sigma square. So if you try to see the center line in the curve, that is actually here mu, and that is the point where the curve is trying to reach its maximum. Right, so that point on the x-axis is actually mu, and in case if you try to find out the mean of this distribution, that will come out to be at mu. So that is why we say, means initially we don't know whether mu is mean or variance or skewness or kurtosis, but when we try to do our algebra, then only we come to know that mu is the parameter that is trying to indicate the central value of the distribution. So we say that mu is the mean. And similarly, the left hand side and right hand side is spread around mu, that is indicating the value of sigma square. For example, I have made here two blue lines which are indicating the points mu minus sigma and mu plus sigma. So you must have heard these words in engineering, means sigma limits, like at 1 sigma limits, 2 sigma limits, 3 sigma limits. So we are simply trying to say that this is the area, or this is the probability that an observation is lying between mu minus sigma and mu plus sigma. So sigma is indicating the spread of the this curve, and you can see here that, well, if you try to do some algebra, you will come to know that the mean and variance of this random variable are actually here, say mu and y square. So that is why we say that mu is going to determine the center of the probability density function, and sigma square is trying to determine its width. Well, whatever is the area of the blue, whatever the this blue color area, right? And you can see here that the point at which it is reaching the maximum, that is also the point of mode as well as median. So normal distribution is symmetric curve. So that is the advantage, that it's a mean, median, and mode. They are the same value. They have got same value here, mu. Right. And if you try to take here mean equal to 0 and sigma square equal to 1, then this probability density function is called as standard normal distribution, and it is given here like this. You can see the expression on the screen. But now the question comes here, what is the difference and why this standard normal distribution became very important in this data science? You see, if you try to look at this distribution, this is depending on the two parameters mu and sigma square that are unknown to us. And if you want to use it, first you need to know the value of mu, then sigma square, and then you can use it. But in this case, if mu is equal to 0, sigma square equal to 1, they are actually practically known to us, and this form, it does not depend on any of the unknown values. So that is why this standard normal distribution started playing a very important role in the statistical inference. And whenever you don't know any value about mu and sigma square, and think about it in practice, you will hardly ever know the value of mu and sigma square. Right, so here I'm simply trying to give an idea that if you try to change different parameters of normal mu sigma square, how it will look like. So if I try to say take here mu equal to 0, that is the mean is 0. And if I try to plot here three possible curves with different values of sigma square 0.5, 1, and 2, then you can see here that the sigma square equal to 0.5 curve is much narrower like this, and whereas with 1 and 2, this is getting more spread. So this is what I wanted to show you, that in this curve, this spread is going to be indicated by the value of sigma square. So higher the value of sigma, flatter the density, right? And more is the variation. Similarly, here I want to show you that what about the different means and different variance. So if you try to see the left-hand curve, where I have made two green curves, you can see here the mean value here is 4, but there are two normal distribution curve with the variance equal to 1 and variance equal to 4. So you can see here that the two normal distributions can have the same mean 5, but they have different type of variance. Right, and similarly on the right hand side, I have made one more curve, which is the copy of the same curve on the left hand side, and you can see here that their variances are going to be the same as sigma square equal to 1, but their means are going to be different. So in case if you have this type of confusion that looking at the value of the means you can conclude about variance, or vice versa, that is wrong. That you cannot do. These are two different quantities. And now the question here is very simple. Suppose if there is a random variable which is following a binomial distribution, Poisson distribution, or any other distribution, that will have always some parameter. And similarly, normal also has parameters mu sigma square. Now, we have just talked about the standard normal distribution. That means the mean is 0 and variance of 1. So the one question is that can you obtain a variable whose mean is always 0 and variance is always 1? The answer is yes. So first I'm trying to state this thing for a normal distribution, and then I will try to extend it to other distribution. So if I say that suppose X is following a normal distribution with mean mu and sigma square, and if you try to define here one more random variable by this here Z, which is defined at X minus mu divided by sigma, that means you take the observation, subtracted by its mean and divided by the standard deviation. Then the distribution of Z will also be always normal, but its mean and variance will become 0 and 1 respectively. And this is called as Z transformation. Right, and this helps us in finding different types of probability statement about X in terms of probability of Z. For example, if you try to see here, means if you try to see that how the probabilities are going to change in this normal curve. So you can see here this green area is trying to give you the limit between mu plus minus sigma, the limits between minus mu plus minus 2 sigma are given by this yellow and light green color. And similarly, if you try to include the blue color also, so that is the range between mu plus minus 3 sigma. So you can see here mu plus minus 3 sigma is trying to cover 99.7% of the area, and yeah, and then this mu plus minus 2 sigma is trying to take 95% of the area, and mu plus minus sigma is trying to take only 68% of the area. So that is how we try to actually work. But now based on this distribution of here Z and this picture, I can now define here a central limit theorem. I can, well, forget about the theory. I'm not going into the theory, so don't get scared about it, because as soon as I take the names of central limit theorem or weak law of large number, people start thinking of complicated algebra. Well, that is my job, and for that I'm getting the bread and butter. So don't worry for that algebra. I'm giving you only here the application. Okay, so in a very simple language, I can say that the central limit theorem tells that the mean of a large number of independent random variables has approximately a normal distribution, and it provides a very simple method for computing approximate probabilities for mean of independent random variables. And I'm sure that nobody has understood this statement. But that's the statement this way. Now let me try to take a very simple example and try to show you what I really mean to say. I will not spend time on explaining this sentence. Well, but just for your information, that this is that here I'm going to consider a very simple form of the central limit theorem that is valid under certain conditions. So, but in case if you are trying to deal with a situation where any of this assumption is not fulfill, then you have to look for another form. And in statistics, we have different types of form. For example, if I say the observations are independent and identically distributed, well, they are coming from the same population and which are expected to have same mean and same variance. Possibly we have one population, but if they are not independent, they are correlated, then we have different type of central limit theorem. And if they are independent but they are not identical, then we have another type of central limit theorem. So I'm not going into that detail, but let me try to give you here a most simple version. Now you can understand it very easily. Let this x1, x2, xn be a random sample from some population. I don't know whether this is normal, binomial, or Poisson. I have no idea. Right, and but I know that that population has got a mean mu and variance sigma square. Right, now I don't know the entire population. And do you think that this condition is very similar to the condition that you encounter in data science? When you have a data of size 30, 40, 50, 100, 200, possibly you can plot it on your software and can plot different types of curves to approximate whether this is normal, exponential, binomial, Poisson, what. But when you are trying to deal with millions and billions of observations and they are continuously coming, can you really know that whether this is binomial or Poisson or exponential? Well, yeah, depending on the condition, you have to take a call. But definitely it is very difficult. So now what we try to do, and then you see in general in data sciences, we are not interested in that individual one. We want to take a conclusions only on the general pattern, and then those conclusions are going to be implemented on the individuals. How? For example, I'm sure that many of you are doing shopping on, say, Amazon or this Myntra, etc. So have you seen that you go to the website, you try to browse some products, some say shirt, trouser, or say camera utensils, and if you don't buy anything, next day you start getting an email that okay, something is waiting in your cart, or this is a coupon code by which you can get a 10% more discount or 100 rupees more off, etc., etc. Do you think that is there someone who is sitting behind the screen of this Amazon who is trying to cater us? That okay, Shalabh wants shirts, so let us give him a discount of 100 rupees, and now Dr. Vanjana Avasthi wants a suit, so she has not bought it, so let us give her a discount of 500 rupees to attract the customers. No, these are automated process. But the main point here is this: what is automated? First, they have to study the general behavior of a customer, and based on that, they have to make targeted forecasting. So general behavior is that usually if you try to say if somebody is of age, say 17 years, 18 years, I doubt if that girl or that boy will be looking for a shirt for his father or sari for a mother or suit for a sister. He or she will be more interested in herself or himself, right? They will be looking for goggles and say this bright shoes, etc. Means I doubt if many people between the age of say 14 years to 17 years, they will be looking for a naughty boy Bata shoes, but they will be going more for the some fancy colorful branded shoes. Right, so that's the pattern. So what they try to do, they simply try to collect the data on the customers who are visiting a particular section. And for example, they want to know the age group that is going through with those sections. So they try to get the data on their ages from their login IDs. And then they try to see that what is the general pattern of the age group of this youngsters, boys and girls. And based on that, they try to give them targeted advertisements and other things. Well, so this is how we are. So they are trying to see the general behavior, that is the average behavior of the customers. Right, so that is why we are very much interested in the average value when we are trying to deal with the data science. So suppose we have got a data, and based on that we can find out the sample mean. So if we have got a data of size 20, then the sample mean is going to be based on 20 observation. And if you are trying to get a data on say 70 observation, then your sample mean is going to be based on 70 observation. And that is what I am trying to indicate here by x bar n. And that is the reason here I have written here x bar and in the subscript n. That sample mean is going to be dependent on the sample size. And definitely if you try to find out the mean and variance of this x bar n, this will come out to be same as mu n, variance as sigma square upon n. So you can see here that as n is increasing, the variability will be decreasing, but that is not my concern here. But what I can say here that if you try to transform this variable by sample mean x bar n minus its mean, divided by its standard deviation, sigma by root n. Well, means if mu and sigma are unknown to us, you can just estimate them by their sample values, mu by sample mean, and sigma square by the sample variance, and try to take the approximate, try to take the square root. That will give you the good approximate value. So now this quantity will also have approximately a standard normal 0, 1 distribution. So now you can see here, although x bar n is depending on mu and sigma square, but x bar n minus mu upon sigma by root n, that is not depending on mu or sigma square. That is independent of the parameter. That is depending only on two values, mean 0 and variance 1. Now, in case if you want to compute the probability of say related to x bar, instead of x bar, I can use the approximate the probabilities using x bar and minus mu upon sigma by root n. Right, so that can be computed, and for that tables are available. You can look into the tables, and in any software these probabilities can be computed without any problem. That's my experience, and I do it. Right, so you can see here that instead of computing the probability of x bar n, you are trying to change the variable x bar and minus mu upon sigma by root n, and this quantity becomes independent of the parameters 0 and 1, and you simply have to just find out that this quantity is being now indicated by here z, that what is the probability of z less than x, and this is available directly from the tables. So you can see here, without doing any integration, differentiation, etc., you can compute the probability for a large sample, means approximate probability, I will say, very easily. So what is happening, that if you try to think about the now for a real data situation, the real data will be suppose following a normal distribution, but I don't know its mean, I don't know about its variance. So we try to simply estimate it, we try to plug in there, and now I want to find out the probabilities related to x bar n, but that is very complicated because we don't know the value of mu and sigma square, the correct value. So I try to convert them into x bar minus its mean divided by its standard error, and then we try to compute the probabilities on compute the probability of this event directly from the normal table, which are available in all the books, and in software you can compute it directly. Right, so now you can compute any type of probability without any problem, without doing any computation. Now if you try to see the advantage, if you try to now read this sentence, let x1, x2, xn be a sample from a population having mean, mu and variance sigma square. That's all. I never said that this is following a binomial distribution or a Poisson distribution or exponential or anything else. I am not also saying whether x1, x2, xn, they are from a continuous variable or from a discrete variable or a combination of them. Nothing. Right, so nothing is said about the form of the original density function. Whatever the distribution function provided, we are assuming that only two conditions, that it has got a mean, mu and variance sigma square. So we are simply assuming that you can use any random variable whose mean and variance are going to be finite. So that is going to be true for most of the cases, unless and until you are trying to take some exceptional case. For example, we have a Cauchy distribution where the mean and variance don't exist, but in general, if you try to take any general probability function, its mean and variance are finite. Also, I'm not assuming that x1, x2, xn are continuous or discrete. But remember one thing, the distribution of x bar minus mu divided by standard error or deviation, it is always continuous. And that's a question where we always try to trap our students. We always say that suppose x1, x2, xn is binomial, which is discrete, but you are trying to compute its probabilities by a continuous function. So how it is possible that a discrete variable can be approximated by a continuous variable? So the answer is very simple. We are not doing it. I should have a courage to tell my teacher, you are asking the wrong question, because we are trying to compute these probabilities from two different functions. x1, x2, xn may have binomial, but now we have changed the random variable, and the transform random variable is going to have continuous distribution, right? Okay, so now let me try to just show you some example that if you have a data, you can very easily compute it. For example, if you are trying to conduct any life testing experiment that you want to see what is the life of a bulb, life of a television, life of a car, life of any component, then usually we use here an exponential distribution, exponential probability density function. So suppose we have drawn a sample from this exponential distribution and we want to compute the probability from this. Although computing probability from this is not difficult, but still I have taken this illustration. So in this case, every random variable will have a mean 1 upon lambda and variance 1 upon lambda square. And now for large n, we've tried to use the central limit theorem and we try to compute the quantity x bar minus its mean 1 upon lambda divided by square root of 1 upon n lambda square, right? And now just for the sake of illustration, that what really happens that if you try to compute the probability directly from here, this exponential distribution, and if you try to compute the probability from this central limit theorem, means after finding out the mean and then transforming it to the standardized variable, what will happen? So what I'm going to do, that I'm going to say generate some observations from the exponential distribution, and then I will try to plot its probability curve, and I will try to generate more than one sample, and then I will try to compute their sample mean, and then I will try to transform them into this by this variable minus mean divided by standard error, and then I will try to plot it. So let us try to see here what do we get here, and that's a real means I have done it myself in the R software, so you can also repeat it. I mean, if you wish, you can just write a small program. So you can see here, that's a very interesting part to explain common user about the central limit theorem. So if you try to see in the first two graphs in the first row, so on the left hand side, there is a heading density plot of means, and the right hand side, there is a heading density plot of central limit theorem. So what I have done, that I have generated the observations, I have computed their arithmetic mean, and then this arithmetic mean is transformed by its mean minus its means value minus mean divided by standard error, and then those values transformed variables values are plotted on the right hand side. So you can see here in the first case, I have taken here capital N equal to 10, means only 10 samples. Right, and you can see here that this is going to be, sorry, and this curve will look like actually here like this. You can see they are a very different type of curve, means they are not looking at least normal. But in case if you try to increase the sample size, now I try to take here 100 samples, means samples of size 100. So you can see here the quantity of plots, it is changing, but now this plot on the second column, this is now becoming more like a normal curve, right? And if you try to increase this value more, this will become here more normal, because ideally the result is for n going to infinity. So that is how, if you try to see the original distribution of the observation from the exponential distribution, they are plotted on the left hand side in the two curves. They are not looking as a normal, but they have their own curve. There is no problem. But in the right hand side, on the second column, both the curves are for the central limit theorem. So you can see here that as you are trying to increase your sample size and you are getting, then this curve is becoming more like a normal and compared to this curve. So now if you have largest sample size, possibly you can approximate the probability from this curve for the same distribution which is here. So that is the advantage of this central limit theorem, because in the data science you will always be getting a larger sample size. So, and in order to compute the probabilities from exponential, Poisson, or any other distribution, that is going to be quite complicated. So the central limit theorem will come to help us. Right. Okay. One thing what you have to do, that when you are trying to approximate the probabilities for a discrete distribution from the center limit theorem, then you have to be careful. Well, yes, discrete random variable has its own properties and continuous random variable has its own properties. And this probability density function is like a histogram actually, that is trying to approximate a histogram. So what we try to do, whatever observations we have, we will try to create the histogram, and then the midpoints of the bars of the histogram, they are joined together by a smooth curve, and that is a sort of estimated probability density curve based on the given sample of data. So now in that histogram, we assume that if we have the class limits like 10 to 20, 20 to 30, 30 to 40, then we assume that all the observations are which are scattered in a particular bar, all are concentrated in the midpoint. Right, so all the observation in the interval between 10 to 20, we assume that all the observation are concentrated only at one point in the mid, which is 15. So what we try to do here, that whenever we are trying to approximate a discrete distribution, okay, what I'm trying to say, suppose you have two options that you want to apply the CLT on a discrete random variable, say binomial Poisson, or you want to use it on a continuous distribution like as we did in the exponential case. So you don't have to do these things in the case of continuous, but in the case of discrete, you have to apply a continuity correction. Continuity correction because the variables are discrete and you are trying to approximate it a distribution of its function of this variable by a continuous one, and you believe that all the values which are concentrated in the bar of the histogram, which are assumed to be concentrated at the midpoint, they are actually scattered in the entire interval. So what will happen if somebody has an age, say 11 years, that will be read as 15, and if anybody has an age, say this 19, that will also be read as 15. So in order to take care of this issue, we have a concept of continuity correction, and what we try to do, suppose if we want to find out the probability that x1 plus x2 plus xn lies between 2 points x1 and x2, so we simply try to say add and subtract 0.5 on the two limits. So just subtract 0.5 in the upper limit and add half in the lower limit. That's all. And after that, you just try to do the same exercise what you have done in the case of center limit theorem. So that will be the difference between the two, that when you are trying to use the center limit theorem for discrete and continuous random variables. Okay. And similarly, if I try to take here one more example, you see either I try to consider sum of the random variables or the arithmetic mean of those values. That is the same thing, because arithmetic mean is defined as summation xi upon n. So either I try to do with sample mean or the sum of the variables, that is not a big deal. Right. For example, if somebody is sitting in, say, this MHRD or say UGC, and they want to see how much grant they have to give to the different academic institution for the salary of the people. So now suppose they would always be interested in the total, that how much total grant they have to give to that institute. Yeah, they are not interested in the mean, that they are not bothered that in a particular college, university or institute, which faculty member is getting what salary. They will simply ask you, okay, tell me the total value. So that is why I have taken this example in the form of sum. So whether it is sum or arithmetic mean, you have to process it exactly in the same way. So suppose we have some sample from a Poisson distribution. Poisson distribution, that is going to be valid where the number of observations are extremely large, but the probability of success or say failure is extremely low. For example, if I say if you try to make a small hole and you try to put there some radioactive material, and then you try to see that how many particles are really crossing through that small hole. Well, there will be, I don't know the number exactly, but there will be billions and trillions of emissions per second. But the total number of points that are crossing through the hole, that will be extremely less. So the probability of success, that the probability that the particle can cross through that hole is very, very less. Similarly, if I try to say, suppose you have a book which is published from some reputed publisher like as Wiley, Chapman Hall, Springer, etc. And there is some book which is published by some local publisher who are not that much professional, means if that is what I mean. Right, then if you try to see the number of mistakes in a page, number of typographical mistakes in the book, what will happen? In the case of, I personally feel, well, I don't know, that the mistakes usually in the Wiley's, they are very, very less. Because as an author, we submit the manuscript and then they also have some person who will try to read it. But now with the spell check also, they can do it very easily. And then the number of mistakes become very, very low. But if there is some publisher who is not that professional, possibly he may not look into those errors, and possibly the number of mistakes will become more in the observation. So that is why if you try to see in our childhood, when we are trying to solve a book, whenever we are trying to solve sort of this problems on the end of the chapter, then at the end, after I will try to match the answers. In case if the book is from a good publisher, reputed book, then if my answer is not matching, possibly I will say, well, I have to look into my solution again. Possibly I have done some mistake. But if the book is from some local publisher, not so carefully printed, then I will say, okay, the solution can also be wrong. I am correct. So these types of events, so where the number of words of typing are very, very large, but the probability of success is very low. Probability of success means probability of the number of mistakes or probability of finding a mistake in the word. In these cases, we actually follow this Poisson case, and that is what is happening. If you try to see, if I now give you one more example, that whenever you are trying to do the shopping on Amazon, Flipkart, etc., means every day there are thousands of people who are shopping, thousands of people who are returning the products, and thousands of transactions are there. If you go to the credit card company, the Masters, Visa card, etc., millions of transactions are happening every day. And you can see that how many times there is an error, that Flipkart has possibly cancelled the item, whatever money you have paid, that is returned, and it is processed by the MasterCard or Visa card, and it comes back to your account after 2 days. How many times have you really observed that there is a mistake? So in these cases, the number of transactions are very high, but the probability of making a mistake is very low. So that is why I have taken this Poisson distribution. Okay, so in this case, suppose if I say that, okay, these observations have been obtained with some parameter equal to lambda equal to 0.125, and we know that in the case of Poisson, the values of mean and variance, they are the same. So now in case if you try to see, if I want to compute the probability that x is equal to small x, which is given by this probability mass function. So suppose if I try to take the sum of, say, this 65 values, say x1 plus x2 plus up to x65, and I want to see whether the sum is equal to 10 or not. Now, in case if you try to find out this probability from this expression, you can compute it using any software, and this will come out to be 0.099. That is the exact probability. But definitely, if you try to make it here n equal to 1 million or 1 billion, I don't know how the probabilities will be computed. Now we try to approximate the same thing using the central limit theorem, and let us see what happens. So what we have to do, this is a discrete random variable. So I have to write down summation xi equal to 10. But now I have to make half number less, means I have to subtract and add 0.5 in the upper and lower limits. So now this 10 is converted into 9.5 and 10.5. Adding and subtracting half number, and the summation xi is going to lie between 9.5 and 10.5. Now we know the value of your mean is 0.125 and variance is 0.125. So what I try to do here, and here is 65. Right. So yes, sorry, I think this and should be here is 64. I'm sorry for the typing. Right, so what we try to do here, I simply try to put it here, this 9.5 minus n into lambda, that is the mean of the summation, and then divided by standard deviation, and you can just, and now the same thing, that means you are simply trying to subtract the mean on 9.5 summation xi 10.5 and divide each quantity by the standard deviation is square root of 64 into 0.125, and this probability can be computed using the normal probability. This capital phi is going to indicate the symbol that this probability is being computed from the probability distribution of normal 0, 1. So this capital phi is actually indicating the cumulative density function. Well, I'm not going into that detail, but these values can be obtained from the table or directly from the software. At least in R, I know that they can be obtained by a simple command here, pnorm. Right, and this probability will come out to be here 0.108. So now that is not my concern to show you this algebra or calculation. But if you try to see, the exact probability is coming out to be 0.099. But when you using the actual original probability distribution. But in case if you are trying to approximate it using the central limit theorem, it is coming out to be 0.108. So you can see here how much is the difference. Not actually much, but the type of computationally it is very expensive. Means if you have a large number of observations, possibly you cannot even compute it. But now using this normal distribution, you can always compute it without making your computationally burdened, right? So this is how, and then and then there is not much difference between these two values, 0.09 and 0.1. Actually, it's not 0.09, it is 0.099 actually. So you can see here that this difference is not actually much, and if with such an easy way and computationally efficient way, if I can compute the probability, what else do I want? And once you have all this probability, you can write different types of distribution and you can compute the probabilities of different types of events, right? So you can now, in case if you try to increase here the sample size. So sample size here is 96 now. In this case, if you try to do this computation, this is coming out to be 0.101. So obviously you can see here with this n equal to 64, this was coming out to be 0.108. And when you are trying to increase from 64 to 96, it is coming out to be 0.101. So this probability has become more precise because they are trying to approximate this 0.099. Right. So if you try to increase the n here more, this probability will become more closer to the true value. Right. And the size of data which you are going to handle in data sciences, that will make approximately the same probabilities. So you can see here that how this central limit theorem can help you. Right. So now I can say very simply that if you have an distribution, or if you have observation from any of the distribution, either it is binomial, normal, Poisson, or say anything, you can just approximate the distribution by the sample mean. Try to take the observations, try to find out the sample mean, and then try to standardize it. That means sample mean minus its mean divided by standard deviation, and whatever probability you want to compute, you can approximate it by the normal 0, 1. So the advantage is now, in order to compute the probability from the normal mu sigma square, you don't need any of the value mu or sigma square. You know the value that mean is 0 and variance is 1. So you can see here that it is not very difficult. For example, if I try to take here one more example, suppose the heights of some students in a university they are measured, and they have got here the average value comes out to be 167 centimeter, and its standard deviation comes out to be 27 centimeter. And suppose we have chosen the 36 workers, and we want to find out the probability that sample mean of the weight lies between 163 and 170. Well, in data science, suppose you are working in Amazon, you would always try to find out that what is the probability that these young children between the age of say 14 and 18 will be interested in visiting the site during this hours, or they will be interested in buying this type of shopping items. Right, so that is what I am trying to indicate here by this simple example. Right. This example I have taken intentionally to means which are very valid in a data science setup. Well, you can find them in undergraduate books also, but that is what I said in the beginning, that now you have to change your thinking process. Actually, this is not the question of subject from statistics to data science, but it's the process of actually thought process. Thought process has to be changed. But in order to change the thought process, first you have to understand the basic fundamentals. Right. So now what I try to do here, that I try to find out here the employ the central limit theorem, and we try to compute this probability that x bar is lying between 163 and 170. Now, in order to find this thing, I try to standardize it. You can see here the mean is 167 and standard deviation is 27. So the standard deviation for the mean will be sigma by root n. So this comes out to be here 4.5. So I try to subtract mean, that is 167 centimeter, in the lower limit 163 x bar and 170. And this is here 163 minus 167, like this in the numerator, and in the denominator I try to divide it by its standard deviation 4.5. So now this quantity x bar minus 167 upon 4.5, that will become here z, which will be following a normal distribution, and these two values on the left hand side and right hand side, they will be 0.8889 with plus and minus signs, and I can compute the probability using a software. So this is the command in the R software. This probability will come out to be exactly here 0.6259. So you can see here that computing from such a big population, this type of probability is difficult, but from normal population you can very easily compute it, and you can say that there are almost 62.5% chances that x bar will lie between 163 and 170. So you can see here, if you want to compute this expression, you just need to write it like this, and then after that you don't need any algebra, you just need to know this command here in the R software, which can compute this value. Right, and this also answers very popular question that many times I see that people are asking me, okay, what should be the sample size for achieving this? Right, so when you are trying to work in the this large data set, it depends actually on the nature of the problems, how complicated it is. If the function that you want to approximate while doing a statistical calculation, if it is very complicated, you will surely need a bigger data size. But if the function is say not so complicated, then possibly you will need a smaller data size. Right. So for example, in the case of this normal distribution, a simple rule of thumb is that one can be confident about using the normal approximation if your sample size is more than 30. It's not a bad option. You can see with 30 observation in data sciences, that means nobody will even think about this, right? So, and then even if the population is not actually normal, this is something very different, but the large sample size and its standardization will make it approximately normal. Right, and so this normal approximation is going to be valid for much smaller size that you handle in the data sciences also. Right, so now I think in the next half an hour, I just try to give you an idea about the estimation of parameters. Why estimation of parameters? Because you see, whenever you are trying to do something in the statistics, you are always interested in finding out the answer on the basis of a sample of data. But what you really want? You want the answer for the entire population. Suppose if I ask you that there is a new medicine, and that medicine claims that it can control the body temperature for a longer time. So for example, nowadays we say that, okay, if somebody has a body temperature, one can use a crocin or paracetamol. So we say that, okay, a crocin can control the temperature for up to say 6 hours. So what is that value? That is the value which the value of the time in which the temperature will remain in the normal limits. But how do you get this 6 value? So for that, what you need to do? You will conduct an experiment. You will take a group of patients, and then you will give them the medicines, and then you will try to see that what is the time up to which the medicine can control the body temperature, and then you will get that data. Okay, now what to do with that data? You will try to find out arithmetic mean, median, or something else. But tell me one thing. You are trying to find the average time of temperature control on the basis of a small set of data, but you are trying to say that it is going to remain valid for the entire population of this world. For example, nowadays you can see this COVID trials are going on. Right. So what people are doing they are going in different countries. For example, this Russia and US, they are conducting the clinical trials. So what are they trying to do? They are trying to collect some people. They are trying to give the vaccine to them, and they are trying to observe the reaction. But how many of the Indians have participated? Indian means those who are staying in India in that clinical trials that happened in US or Russia. But as soon as they get a clearance from their FDA, Food and Drug Controlling Authority, the Indians will also get the same vaccine. Now, can you tell me that how it is possible that they have taken, say, a couple of hundred people from US and that vaccine is going to be valid for all the people in this world? How it can be possible? Right. So that is the thing what we are trying to do in the statistic, that how we need to take the statistical conclusion which are valid for the entire population and not only to the samples. So whatever you are getting on the sample, how to ensure that that is going to remain valid for the entire population. So now this is actually called as estimation of parameters. Right. So we have different types of properties of these estimator, like unbiasedness, consistency, efficiency, etc. So that we try to check whether my estimator is good or bad. But at this moment, in the next half an hour, I cannot give you those details, but definitely I can give you an idea that how are you going to estimate those parameters. And if I ask you a very simple example, you try to give an answer to yourself, and I will verify it after I explain you. Well, in case if I ask you that how much time do you take from coming to your home and your office or your college, you will certainly have some value, 20 minutes, 40 minutes, 70 minutes. But my question is what you have done, how you have computed, or how have you arrived at that value, 40 minutes or 60 minutes. Surely you have done something in your mind. My question is what you have done. Whether you have taken the arithmetic mean, geometric mean, median, mode, or what else. So usually the answer that I expect will be that you have simply collected some data inside your mind. As soon as I ask you a question, you just collected the data that, okay, in the last 15 to 20 days, how much time you have taken. And suppose it was sometime 30 minutes, sometime 35 minutes, sometime 40 minutes, sometime 25 minutes. So you have just taken the arithmetic mean of those values and you have told me that the average time is 30 minutes. But my question is, who told you that you have to take the arithmetic mean? That's my question. Who stopped you in computing the arithmetic, this geometric mean, harmonic mean, or median? You cannot say that this is computationally easy, because even if I ask you 10 values, say 30, 25, 28, 27, 32, 46, 44, 43, you cannot even compute the arithmetic mean right now. But your brain has given you a very good value, say 30 minutes. How this is coming? So that I will try to answer towards the end of the lecture, right? So anyway, so I'm going to discuss about here two possible estimation methods which are going to help us in estimating the unknown parameters of the population. So one here is method of movements. Well, I'm not going into the detail of the method of movement, but I believe that these are that you might be knowing, and if not, these are very simple quantities, some statistical quantities. They are trying to indicate the characteristics of the data. For example, the first movement is indicating about the mean, second movement is about the variance, third movement is about the skewness, fourth movement about the kurtosis, and so on. So if you try to see here that you simply try to take a special type of expectation, like expected value of x minus a to the power of r. So this will be called as rth moment of x about the point A, right? And if you try to take it here equal to 0, this is called as the rth raw movement. But definitely this quantity is based on the population, so we try to define it on the basis of random sample or random observation. So this is, you can see, this is a very simple quantity. 1 upon n summation I goes from 1 to n xi is the power of here r. So you have the observation x1, x2, xn. So you try to take their arithmetic mean, or you first try to square them and then try to take the arithmetic mean. That will give you second raw movement. If you try to take the cube of those observation and then try to take the arithmetic mean, that will give you the third raw movement, and so on. And similarly, if you try to compute this quantity, 1 upon n summation I goes from 1 to n xi minus x bar raised to the power of here r. That means you try to take x1, x2, xn and try to subtract every observation from the sample mean of those observation, and then try to take its mean. That will be called as first central movement. If you try to square the xi minus x bar quantities and then try to take the arithmetic mean, that will be called as a variance, and so on. So these are called actually central movements. So anyway, that is just a small background. Now let me ask you one thing. Suppose you want to purchase some wheat, and we have seen the godowns for the wheat have this much of wheat, or there's at least 100 kg of wheat in a bag. How do you come to know whether the quality of the wheat is good or bad? So what you try to do, you will try to take a very small sample. It means I have given you here two pictures. There's a small instrument that you try to put it inside the wheat bag, and you will get, say about 20 to 30 grams of wheat. You try to look into your hand, and or you can just take a small sample in your hand and you try to check what's the quality. Right, and sometimes if you are intelligent, you will try to take a sample from the top, from the bottom, and from the somewhere in the middle also. Now, what do you do? That is my question. You simply try to look into the number of grains which are good in the sample. And now there can be different situations. Suppose you get suppose 100 number of grains in your sample in your hand. And suppose if you say that 50 grains out of 100, they have got a hole, that means they are infected by some insects. What do you conclude? You conclude that this bag is bad and at least 50% of the wheat is bad. But if you try to see that only there are 20 out of 100 grains which are bad, then you say that, okay, I think in this bag, 20% of the grain is not good. But on the other hand, if there are no grain which has got a hole, then you simply say that, okay, this bag is good, and you expect, remember, you expect that the quality of the wheat in the entire bag is the same. So what are you trying to do here? Try to just think about it. You are simply trying to make a one-to-one connection between the properties of a sample and properties of the bag. You are saying that, yes. Yes. Okay. So, and then what you are saying that whatever is existing in the sample, the same thing is existing in the population also. So whatever are the properties which are existing in the sample, they are mapped with the properties inside the bag. So now in statistics, we have these movements which are trying to measure the different properties of the statistics, different properties of the variable, right? Like as mean, variance, etc. So what you try to say that whatever is the mean of the sample, you expect that the same mean will continue in the population. Whatever is the variability in the sample, that variability is going to continue in the whole population. Right, and yeah, that's a basic fundamental assumption in statistics that is nowhere written, but it is always assumed that sample is a representation of the population, that whatever are the characteristics which are available in the population, they are also available in the sample. That is the basic assumption. So based on that, what we try to do here in the method of movement, that we try to compute the movement on the basis of the sample, and then I try to equate it to the movement of the population. For example, first raw movement equal to the first raw's movement based on the sample. Second raw movement of the population, that is equated to the second raw movement that is computed on the basis of the sample. And then we have some equation and we try to solve it. Those estimators are called as method of movements estimator, and they will give you a good value of the unknown parameter. Right, so let me try to take here rather this example and I try to show you here. So I am taking here one example so that I can convince you. Suppose you have a sample from a normal population with mean mu and variance sigma square. Right, so here is mean, here is mu, and variance sigma square, and both are unknown. So what we try to do means I have got here two parameters, so I will try to compute first two raw movements based on the sample and based on the population, and I will try to equate them. So with this I'm trying to indicate the sample movement, and with the first sample movement is simply your arithmetic mean, and this population first raw movement here is mu. So I try to equate here x bar equal to mu, and then I try to equate the second raw sample based movement with the second raw population based movement. So the second, well, these are the statistical thing, you don't have to hurry. So I try to find out the second raw movement as if 1 upon n summation I goes from 1 to n xi square, and I try to equate it to the second raw movement from the population, which is mu square plus sigma square. Yes, how it is coming, that can be your question, but that I can solve and can show you. That's a very simple algebra, and that's our bread and butter. Right, as simple as that, I would say. And then I have here two equations, x bar equal to mu and mu square plus sigma square equal to here this summation xi square. Now if I ask you that you simply have to solve these two equations and then you have to get the value of mu and sigma square, do you think is it very difficult? You can see here that here from itself you can get it here mu equal to x bar. That means if you want to know the value of population mean, then you simply have to compute the sample mean, right? And if you want to, once you compute the sample mean from here mu, that is x bar, you try to replace it here in the mu square and then try to find out the value of sigma square. And if you try to do it, this will come out to be the value of the mean will come out to be capital X bar, and the value of the variance will come out to be like this 1 upon n summation I goes from 1 to n xi minus x bar whole square. So don't you think that this definition of the sample variance or the variance that is based on the sample is very much similar to the definition of the variance that we have been taught right from the beginning? So what now I'm trying to say? Well, the real values of mean and variance, they are unknown to us. But now what I have to do, I simply have to take a sample, and from the sample I have to find out the sample mean. And this is here the sample mean, and then I have to find out the sample variance from this expression, and then whatever are the values that we can accept as very good values of the unknown parameters mu and sigma square, and they are called as, say here, method of movements estimator. Well, they have different types of properties. For example, I want to address here that when we are trying to estimate the sigma square, then I have two forms here. The divisor is 1 upon n, or the divisor here is 1 upon n minus 1. So, well, the only difference between the two is that they are that this estimator with the 1 upon n, it is a biased estimator of sigma square, and 1 upon n minus 1 is an unbiased estimator. But for a practical purpose, that doesn't make much difference for you, because you are going to work in a bigger data set, and then either you are trying to divide it by 9,999 and 10,000. That is practically not really going to make any difference. So you can see here that now using this methodology you can actually estimate the unknown parameters, and these things can be applied to different types of probability function, probability density function, probability mass function, because your population is going to be characterized by some population. For example, I can say the behavior of children for shopping is very much different than the behavior of the shopping of the elder people. So these are going to be defined by two different probability distributions. Right, okay, so now I try to briefly give you an idea about the method of maximum likelihood. This is one of the best methods to obtain the point estimator, and this was developed by the father of the statistics called as R.A. Fisher. And as the name implies, the estimator will be the value of the parameter that maximize the likelihood function. But forget about these things. Let me try to ask you a very simple question. Suppose I am coming to your place and I want to travel from your home to the railway station, and it is and I have got a train at 5:30 in the evening. That is the office time. So the traffic is going to be heavy, and I ask you that I have just 45 minutes in my hand. And suppose your home is say about 7 to 8 kilometers from the railway station. So now I have to go to the railway station. I have a couple of options. For example, I can walk, I can take an auto rickshaw, I can take a car, or even I can take a simple cycle rickshaw also. What are you going to suggest me? You will simply tell me, okay, take this Miss auto rickshaw, for example. And if I say that, okay, I have to go at 5 o'clock in the morning when there is no traffic, you can say that, okay, you can take a car, right? That will easily reach you there without any problem. But during the office time, your apprehensions are that there can be a traffic, and based on that, there can be this traffic jam, the roads are going to be narrow, etc., etc., etc. You try to do something inside your mind and try to tell me that, okay, this is the most appropriate vehicle that you can use. Now my question is, what are you really trying to do inside your mind? That's my question. So, in fact, what are you trying to do? That you are simply trying to take one way of transportation at a time, and you are simply trying to computing the probability that if I go by auto rickshaw, what is the probability that I will reach there within 45 minutes, and what is the probability that if I walk, then I will reach station within 45 minutes, 8 to 9 kilometers. And then if I take a car, then what is the probability that I can reach the station in the 45 minutes? So obviously, if the traffic time is there is going to be a traffic. Then possibly if you go by car, there is a good chance that the speed may be low and you may get trapped into the traffic jam. So the probability may be something around 30% that you will reach the station in time. Similarly, if you try to walking 8 to 9 kilometers with the luggage and you can reach there in say 40 minutes time, it is usually a little bit difficult. So the probability there is only say 40% that you can reach there. But if you take an auto rickshaw, possibly the auto rickshaw has an advantage that it can go to a narrow lanes. Possibly it can drive at a reasonable speed. Even if there is a traffic jam, it will try to take you here and there, and finally you will reach to your station. So the probability that you will reach to station by taking an auto rickshaw is more than say 80%, 90%. So now based on that, what you have done, you have computed the probabilities of auto rickshaw 90%, by walking 40%, and by taking car 30%, and whatever is the maximum probability according to which whatever is the way of transportation you have informed me. And in this case, this is coming out to be the auto rickshaw. So that is why you have suggested me better you take an auto rickshaw. Right, so this is how you try to do. So if you try to see what exactly are you doing, you are simply trying to compute the probability of an event, and then you are trying to tell me you have got some data. Based on that, you are trying to compute the probabilities, and then you are trying to tell me the value of the mode of transportation which takes the for which there is a maximum probability of success or the happening of the event. So can't you do the same thing in the setup of data? And that's the thing which you are doing every day. If I count, not less than 100 times. Sometimes means I ask you, okay, your friend is coming. Oh, he will come 5 minutes late always. He has not even come, but you have branded him that he will come 5 minutes late. And for someone, oh no, we have to reach in time because he is always there at 5 minutes before. Right. For example, for me, a student commented that if you reached 2 minutes late in my class, possibly 2 blackboards are finished. Means two times writing on the blackboard is already finished. So they will run if they have a class that dot is 11:00. They will try to zoom into my class. Otherwise, they know that the class is going to begin. So what are we trying to do? They know that for this teacher, I have to run. For this teacher, I can walk. So every day we are trying to use this method in our day-to-day life. Right. OK, so now let me try to do what I'm going to do here. It is very simple thing. I'm trying to observe a sample from a given probability density function. And then I'm trying to find out their joint probability. Well, there are methods by which you can find out the joint probability. For example, if I assume the independence of the observation, the joint probability function can be obtained just by multiplying all the PDFs. And then I'm trying to write down this joint. Actually, this joint probability density function is called as likelihood function. And you know that what are the likelihoods that this person will come to office today? What are the chances that this person will come to office today? So likelihood and this probability or chances, they are the same thing. Right. So what are we now going to do here? We are going to observe the sample values, some numerical values, and we try to put it there and we try to find out the value of theta for which this probability is maximum. So likelihood function is actually a probability function. So what we try to do here, that we observe the data, we try to compute the likelihood function, and then we try to find out the value of theta for which this probability is the maximum. And that is why this is called as, and whatever the values you are going to get for the theta, it is called as maximum likelihood estimated. That means this is the value of the parameter which is going to give us the maximum probability of the selection. For example, if you take the modes of transportation to be auto, then this is going to give us the maximum probability of success. That's all, as simple as that. Right. So if you try to see here now, let me try to take a very simple example and can try to show you here that if you have a.
I have a question, sir.
Yeah. Can you just give me 1 minute? I'm just going to finish it. Hello. Yeah, I'm just going to finish it. Right. So in case if you simply toss a head and tail type of experiment, this Bernoulli distribution, in that case, you want to on the based on a sample of data, you want to on the probability of success or failure, that is actually here P. So for that, I simply have to write down this function. I have to just differentiate it, or actually I have to optimize it. I have to maximize this function. Sometimes you will see that instead of maximizing the original function, the log of the function can also be maximized, because log and the original function, they are monotonic. So if you try to plot them here, this is the likelihood function as such, and this is here the log function. So since we are interested only in the maximum value, so the maximum is going to occur at the same point, either you try to take the function or the log function, right? So that is why I try to take here the log function. I simply use the class 12 or say BSc part 1 technique, principle of maxima minima. I try to differentiate this log of L and try to find out the value of P. This comes out to be here sample mean X bar. And if you try to go for the second order condition also, this will also hold true. Right. So you can see here that this sample mean is coming out to be the value of the parameter, which is going to give us the value with the maximum probability. Right. Similarly, if you try to take your normal distribution, normal distribution has two parameters, mu and sigma square. So we try to write down the likelihood function and then we try to differentiate it with respect to the parameters, and we obtain that the maximum likelihood estimators of mu is sample mean. And the maximum likelihood estimator of sigma square is like this, 1 upon n summation I goes from 1 to n x bar whole square. After that, yeah, we have to make sure that this principle of maxima minima is going to give us the maximized value. That means these values are going to maximize the likelihood function. So now at the end, I can say very simply, it is trying to tell me that if you have a sample x1, x2, xn from a random, from a normal population with mean mu and variance sigma square, and you don't know any of these value, simply try to observe the sample and try to compute the arithmetic mean. This will give you a very good value of the mu. And if you try to compute the sample variance, it is going to give you a very good value of the sigma square. And now if you try to see, when I asked that question, that how are you going to tell me whether that it is going to take 30 minutes, you computed the arithmetic mean. So now you can see mathematically also we are convinced that arithmetic mean is going to give us the value which is very close to the true value. And that is what I say, that when God created us, then God has install a very small IC transistor or some machine inside our brain for the statistics. The only thing is this, we never try to think about that, but we know how to use it. Right. So this statistics is only trying to ensure that whatever you are thinking, that is on the correct line. Because when we are educated, means anybody can be wrong and say anybody can be right. A logic can be wrong. A logic can be right. It depends only when we are able to prove them in a mathematical way, in the correct way. If I can prove somehow that coming to office is a good thing, then everybody will come to office. And if I'm able to prove that coming to office every day is a bad thing, then everybody will say that, okay, coming to office is a bad thing. So now we have logically and mathematically shown that the sample mean is coming out to be a good estimator. That is why in most of the cases we are trying to find out the arithmetic mean. But when there is some other process, you will try to employ something else. For example, in the case of COVID, nobody is able to forecast that when the COVID is going to over, because we don't have the data. That's all. If we had the data, we can do it very easily. In the last seven to 8 months, everybody in this country has become a COVID scientist. Everybody has become a statistician. Means on Facebook, on LinkedIn, there is a flood of papers which are trying to forecast the COVID, but they are all rubbish. Let me know, because there is no data, so how can you forecast it? The only thing is this: you have to pray to God, do the tapasya, go to your Himalaya and ask the God. Unless and until there is a data, no statistician can do any type of forecasting. So now I would stop here. If you have any more questions, you can ask. I will be happy to answer them.
Sir, I have a question, sir.
Yes.
Sir, in last example, we can, according to example, we can identify if the data is parametric or not, if the attribute are keep on changing or not. So how will we came to certain decision to take certain test for that data? Like if it is a non-parametric, how we will decide that a binomial test is better or Fisher test is better, or if it is a parametric inferential statistic data type of data, how will we identify Mankova test is better or ANOVA test is better?
Okay, good question, but a very detailed answer. I will try to make it as short as possible. Yes, we have two types of setups, parametric and non-parametric, and I have not talked anywhere about the non-parametric inference. If I talk about non-parametric inference, then it is going to be a different type of a story. I have taken only here only the parametric part. Yeah, your organizers have given me only 1.5 years to speak, so that is why it was not possible for me to speak on all the things. So that is why this was only to the parametric part. Well, just to let you know, if you don't know that you have got a normal population or any type of PDF cannot be confirmed, PMF cannot be confirmed, where you don't know what is the form of your population, then you try to go for non-parametric part. Here I'm assuming let x1, x2, xn be a sample from normal distribution with mean mu and variance sigma square. That is why this is a parametric setup. So we are dealing only here with the parametric setup. Whenever we get the data, there are some statistical tests by which we try to first see whether this data is following the normal distribution or a binomial distribution or something else. For example, there is a graphical way that is called as QQ plot, quantile plot. If you just plot them, they are readily available in any software. They will give you a fair idea whether your sample is coming from a normal population or not. Right. What was the third question? There was a third part of your question. I just forget it.
Sir, my question was simple, that how do we decide between which test to apply on that data?
You see,
like in last.
okay, yes, got it. Tell me one thing, Ritik. I'm sure that when you come to your college and when you go to your friend's marriage and when you go to your brother's marriage, do you know what to wear and what to not? Suppose you have a say shirt of color, say sky blue like me, or a color say some printed say red color, and there is some sort of sherwani with some golden embroidery. Do you know that which of that you are going to be?
There is no specific theme to the party, but according to the
pardon?
There is no there is no specific theme to different parties, but according to the gathering, we can decide that if we are going to the wedding, we are going to be formal or
answer. I'm just asking you to tell me you have these three type of shirt. Which of the shirt are you going to wear in these three occasions?
So for wedding, I am going for formals, and if I am going to the birthday party, it informal will be better option.
How do you decide?
So according to the audience, sir.
Yeah. So according to the means, according to the occasion, according to the need and requirement.
Yes,
right.
Sir.
Exactly. The same thing is in statistics also. Different tools are going to be used under different types of situation. When somebody has a problem in the say skin, that goes to a skin specialist. If somebody has a problem in the ear, that person goes to ENT specialist. And if somebody has a problem in the stomach, he will go to a physician. So similarly in statistics also, we have variety of tests, and we try to and then every test is going to be used under a particular type of situation. So we actually, that is what we teach in statistics, that under what type of conditions you are going to test what type of test, whether this is ANOVA or say multivariate ANOVA, MANOVA, or say anything else. So that is, so every test has some desired condition under which it has to be applied. But in 1.5 hours, I cannot explain you means each and everything. But definitely that you know before implementing the test that whether it can be applied or not, which is dependent on your objective and the nature of the data.
Thank you, sir.
Right, so I think no more questions, so I will take a leave from all of you. It was really a nice experience to talk to all of you.
Thank you, Prof. Sir. It was actually a good talk, and I hope the participants, they at least had an idea in such a small time, in 3 hours, you can just introduce them to a subject. Absolutely. So that later on they can actually dive into the various details. Correct. And understand where what can be applied. Thank you very much for your talk. Hope to see you some other time again.
Sure. Okay. My pleasure.
I think there is a question from Mr. Vikas.
Yeah, sure.
Thank you very much, sir, for your time and the session. It was really wonderful. Can you please help in sharing this PPT so that it would be a great help for us to.
Why not? Why not? Why not?
Yes,
Why
yes.
not? I will
If you can
send
share
it
the
to
PPT, that
Ranjana.
will be great. Yeah.
Yeah, I will
You please mail it to me. I will share it with them.
Sure.
And another thing, this is Tapas here. If I want to be in touch with you somehow, how will I do that?
You see, you have a faculty in your institute who once decides that she wants to get in touch with me. She can get many things done from me. Believe me, today I had to do my recording. I have a MOOC course which I am going to float from January. More than 12,000 students are already enrolled and my recording is not yet completed, but she forced me to give this lecture.
Okay.
Right, so you can just contact her, she will get it done.
All right.
Thank you, Shalabh. Thank you for taking out time for me.
Thank you.
Okay, thank you very much. You
Bye.
can, if you want, you can take a leave and
Yeah,
continue with your recordings.
Sure, right.
Yes.
So participants, we also take a break now. We'll meet at 2:30.
Sure.